welcome everybody. So this last part of the solutions chapter is going to talk about oxidation reactions, reduction reactions, or as they're put together, redox reactions. And it's also going to talk about how to do some of the math that we kind of have been getting into, but here are the notes on that stuff. So for oxidation reduction reactions, you first have to understand how to apply oxidation numbers. And oxidation numbers, depending on what you actually are dealing with, can mean different things. Like for example, if we look at rule number 1 here, we can break this rule up and we can say, well, for elements alone, they have no charge. That means that they're neutral. If we have an ion that's monatomic, then the oxidation number is equal to the charge of the ion. So what does this look like? Well, if I had Na by itself, the charge would be 0. If I had Na plus, then the charge would be plus 1. Well, what happens if I have a compound? Well, if I have a compound, we could have a few different situations going on here. So if I have a compound, and it's a neutral compound, the oxidation number could be the apparent charge if you're covalent, or the actual charge if the compound is ionic. So what do I mean by this? Like if you had something like SO3, for example, well, with SO3, this is covalent. O, if you remember how to do this, O is -2. The total for O is, there's 3 of them, so it's -6. It has to add up to 0, so the S would have to be +6. -6 plus 6, they would cancel out. S would be +6, O would be -2. Now this is an apparent charge because it's not an ionic compound. They're sharing electrons. But since O is more electronegative, you give it the negative apparent charge, the negative oxidation number. And really, what they're looking at with oxidation numbers when they talk about apparent charges is, what would the charge be if the compound was ionic? In a way, these apparent charges are made up. If I had something that was ionic, though, like NaCl, well, Na would be +1, Cl would be -1. If these were real charges, this is an ionic compound. Now, what happens if I have a polyatomic ion? What happens if I have like SO3 2-? Well, now we have this polyatomic ion. It's still covalently bonded, though, so it's still apparent charges. But now the total charges is equal to the charge of the ion. So if we had this case, if we did SO3 over here, it would be equal to -2 in this case, because the charge of the ion is -2. If we then went ahead and did the oxygen, well, the oxygen's -2. There's 3 of them, it's -6. Now the S is no longer +6, it has to balance out to -2. So the S would be +4. So these are the first 2 rules of assigning oxidation reduction reactions. What about general rules for elements in a compound? What if we were to base it on the periodic table? I don't know if you learned this last year, but you can go by group number. If you're in group 1A or group 1, 2A or group 2, 3A, which is group 13, 4A, group 14, 5A, 15, 6A, 16, 7A, 17, then your charges can range. If you're in 1A and 2A, you're going to be +1 or +2. 3A, you're going to be +3. But once I get to 4A, I have a range of charges that can take place. So for 4A, for group 14, the range can be all the way from +4 down to -4. So it could be +3, +2, +1, -1, -2, -3, -4. 5A can range from +5 all the way down to -3. Group 6A can go from +6 all the way to -2. Group 7A can go from +7 all the way to -1. Now, there are a few exceptions here that will make, oxidation numbers, a lot easier to assign when you have a compound. And one of them is the oxygen rule. So oxygen is always -2 in a compound, except when it's in a peroxide. The peroxide, oxygen's actually O2 -2, which means oxygen is really -1. The other one is O with fluorine, OF2. Again, this is a covalent compound. The charges, the oxidation numbers, are apparent charges. They're not real charges. And so because of that, you go by electronegativity. The F is more electronegative, it's -1. The O is going to be +2 in this case, so O will be +2. And the other exception is when you have hydrogen. Hydrogen is always +1, except in something called a hydride. And with a hydride, you have H-1. And this is for a metal hydride, so NaH, KH, CaH2. You didn't need the parentheses, but I did it anyway. So now, as far as assigning oxidation numbers, I want you to practice some of these. I'm going to give you some compounds to do. Let's see if you can actually go ahead and, go through and assign the oxidation numbers. I'll list them up here, and then I'll go through oxidation reduction reactions. So let's say, for example, if I gave you something like KMNO4. How about CuSO4? How about H2O2? How about NH3? I will do one more. How about PbNO3 too? So give some of these a try. Assign the oxidation numbers. If you're really having trouble, we can go through and practice. But this should be a skill that you know really well from last year. So let's talk about how we would do half reactions, oxidation reduction reactions. Let's take, for example, if we were to have magnesium placed into some silver nitrate. And there's a single replacement that occurs. The magnesium dissolves and the silver materializes as a solid. And so the first thing I want to do when I do an oxidation reduction reaction is I want to assign oxidation numbers. So 0, +1, +5, -2, +2, +5, -2, 0. Notice an element by itself is 0. The Mg is in group 2. In a compound it becomes +2. The oxygen is not with one of its exceptions, it's -2. The nitrogen didn't change. The second thing that I do is I look for elements that change their oxidation number. And so I notice here that magnesium changed, and I also notice that silver changed. And I write what's known as half reactions. So if I go through and I write a half reaction for this, I would have my Ag+. I pull it out of the formula, and I have it go to Ag0. There's a difference of +1 between them. So I need to add electrons, and I add electrons to the more positive side. So I would have +1 electron. Ag+, +1 electron yields Ag. I do the same thing for magnesium. Magnesium started off as Mg0, and it became Mg+2. I see there's a change of +2. It lost 2 electrons. I show those 2 electrons on the more positive side. So as a tip here, make sure that you always add electrons to the more positive side of the half reaction. Now when I look at this, I see that the Ag, it actually, was positive, it gained an electron. That's a reduction. The magnesium, it lost electrons, so it is oxidized. Now the problem is that they're not balanced. They need to lose and gain the same number of electrons. So in order to get that to happen, I would take my silver and I would multiply the entire reaction by 2. That would give me 2 Ag plus 2 electrons yields 2 Ag0. I can now add these together for a net ionic equation. Mg0 plus 2 Ag plus. The electrons will cross out. On the other side, I'll have Mg plus 2 Ag0. Notice the number of atoms, 2Ag and 2Ag, is the same. And the charges on the left plus 2 and on the right plus 2 are the same. If you, want to remember a way of, okay, how do I know if it's oxidation or reduction? One of my students told me anger. So that's a negative, gain electrons, reduction. So if you become more negative, you gain electrons, it is reduction. And then pole, positive, oxidation, loss, electrons. So let's see if you could give this a try. Let's try another one, see how you do with this. See if you can write out the half reactions. Let's try something like aluminum plus copper chloride yields aluminum chloride plus copper, unbalanced. So see if you can write the oxidation half reaction, the reduction half reaction, and the overall net ionic. This is actually down here copper and silver reacting. And what's really cool about this is that it actually has the silver materializing on the copper, which I think is great to see. And this is what would happen in our reaction up above here. The silver would actually materialize on top of the magnesium. The magnesium would start to disintegrate and dissolve. Okay, well what about redox reactions where you have acids? Because these are actually quite common. And so one type of reaction is where you have, a metal like, magnesium or zinc, use a new metal, zinc, and you add it to an acid HCl, and you will actually oxidize the zinc. It will become ZnCl2 aqueous, and you will produce hydrogen gas. And we did this lab last year, and you capture the hydrogen gas, and then you put a little burning splint in there that makes a popping noise. And so, here's my zinc. My zinc is oxidizing. It's becoming Zn plus 2. My hydrogen is being reduced to H2. This one's a little bit interesting to balance because I need to balance the hydrogens first before I start doing electrons. I have 2 hydrogens. And so now when I balance this equation over here, remember I add electrons to the more positive side, and the same thing for the hydrogen. I would add 2 electrons to the more positive side, and now I would add them up. And when I add them up together, I would get zinc plus 2H plus yields Zn plus 2 plus H2. Now what if I have an acid that's a nitric acid, and this one's kind of a really cool compound to look at and how it reacts with metals. And so if I were to take copper and put it into something like nitric acid, it actually will react with the nitric acid. And it does so for different reasons than the one up above here. In this case, what's happening is there's a reaction with an actual nitrate ion, and you get copper nitrate. You also produce water, and then you unfortunately produce this brown toxic gas, NO2. This one's going to be more complicated to balance because you're going to need to know how to write half reactions in acidic conditions, and we'll do that later on in the year. But this is just something interesting to look at. Most acids react with metals by producing hydrogen gas and oxidizing the metal. When you have nitric acid, though, nitric acid oxidizes the metal by actually reducing the nitrate and forming this poisonous NO2 gas. This is an activity series. Oh, that's on the next slide. Here is magnesium and hydrochloric acid. Go ahead, balance this one. Write out the half reactions. Oxidation half reaction, reduction half reaction. Let's see what you do with that. But here's an activity series. I show you right here. There it is. So this is like table J. And so what this is showing is that these metals up here, these are easily oxidized. They're very reactive. And down here, these metals over here are easily reduced. So if I put these metals together, like I were to put lithium and then put it into a copper ion that could be reduced, they'll react. The lithium will be oxidized, the copper will be reduced. If you want to tell if a reaction will occur or not, you have to look at the reactivity series and figure out, is the metal that is more reactive being oxidized? Is the metal that's less reactive being reduced? We'll practice some of this in class too. We'll go through some examples of this and practicing using this. Alright, so this video actually went on a little bit longer than I was hoping for. I'm going to stop this and break it up, and I will do the stoichiometry of solutions on the next video. Thanks so much.